Welcome to the second video on Chapter 6. We're going to begin with 6.3, which is Pythagorean triples. And so a Pythagorean triple is basically a set of three integers that satisfies the Pythagorean theorem. So if I have a triangle here, it's a right triangle. Basically, what a Pythagorean triple is that you'll have three sides here that fulfill the Pythagorean theorem. So if I have sides 3, 4, and 5, which is one of the most common Pythagorean triples, then this satisfies it because you have 3 squared plus 4 squared is equal to 5 squared, because 9 plus 16 is equal to 25. So this is what a Pythagorean triple is, and there's many different types of Pythagorean triples. There's the commonly known 3, 4, 5 Pythagorean triple. There's also the 5, 12, and 13 Pythagorean triple, or the 7, 24, and 25 Pythagorean triple. There's also the 8, 15, 17 Pythagorean triple. And so this number right here is always going to be the hypotenuse, because remember, in a right triangle, the hypotenuse is the biggest side. And so basically, these are the hypotenuses, and these two numbers are the legs. So we also then have the 9, 40, and 41 triangle. And so these are just some of the common Pythagorean triples that you're going to see, and I'll go over a problem now. So I've drawn up problem 6.14, and so it's a two-part question. First, they ask you to find the missing sides of each right triangle shown here. So the way we're going to do this is you go, okay, so you want to find AC, E, F, G, H, and X, Z, because these are the sides you want. And so the way you do this is you go, okay, so I have these, and then you just gotta think Pythagorean theorem. So AC is equal to the square root of AB squared plus BC squared, because it's the hypotenuse, and so the two legs squared is equal to the square root AC squared, and so square root that, and then you got it. So you have square root of 9 plus 16, which is equal to square root of 25, which is equal to 5. And so AC is 5. And you just sort of do the same thing for EF here. So EF isn't the hypotenuse though. So you think, okay, so it's going to be the square root of the hypotenuse, dF squared, minus dE squared. Because dE squared plus EF squared is equal to dF squared. So you just gotta think, okay, so minus it and you're gonna be left with EF. So then you get that is the square root of 64, which is equal to 8. So EF is 8. Then you want to find GH here, and it's the same as EF, it's a leg. So you go, okay, so it's the square root of GI squared minus HI squared, which is equal to the square root of 144, which is equal to 12. So GH is 12. Then XC. XC is equal, because it's the hypotenuse like AC, it's equal to XY squared plus YZ squared, which is equal to the square root of a really big number. You can do it on your calculator if you have one, but it's a really big number. But what you're going to get is equal to 555. And so it's 555. And that is because if you look at these triangles, they all have that 3, 4, 5 triangle thing in common. So this is just 3 times 111. This is just 4 times 111. This is just 5 times 111. So that's how I knew, without even knowing what number this is going to be, that's how I knew that this was going to be 555, because it's just a 3, 4, 5 triangle. That's the same with all 4 of these triangles. And then, so that's how you can solve the first part there for finding the missing sides of a triangle. And then you can use this for any Pythagorean triple that you find. If you know it's a Pythagorean triple, because it's a right triangle and you have two sides that fit a Pythagorean triple, then you can sort of find out how big the sides are if you have to. So the second part of this question asks that given A, B, and C, which is a Pythagorean triple, so if you have a triangle like this side would be A, this side would be B, and this side would be C. So if you have triangle ABC like this, and it's a Pythagorean triple, they say, is basically a triangle that's 2A, 2B, and 2C, also Pythagorean triple, or is also NA, B, and NC. So basically, is that a Pythagorean triple as well? And so just looking at what we just did, you can sort of just think, yeah, it looks like it's a Pythagorean triple. So the way they do that is, if it's 2a, 2b, and 2c, you go, okay, so a squared plus b squared is equal to c squared, because it said it was a Pythagorean triple. So then 2a squared plus 2b squared is equal to 4a squared plus 4b squared, which is equal to 4c squared. And because a squared plus b squared plus c squared, which is equal to 2c squared. And so it doesn't really matter how you look at it, as long as it's like these problems up here, and I just explained down there, as long as it's the same number in front of it, then it's fine, it's a Pythagorean triple, and it remains that way. And so you get that sense with this up here, as long as n is the same number, and it's a Pythagorean triple already, it's going to remain a Pythagorean triple. So if it's a 3, 4, 5 Pythagorean triple, it could be a 6, 8, 10, like this one right here, or a 12, 16, 20. Doesn't matter what it's, as long as it's the same number multiplying this Pythagorean triple, it remains a Pythagorean triple. And so that's one way you can see if you find a triangle like this. And so that's how you do problem 6.14. And if you want to see the rest of chapter 6, I'm going to do 6.5 or 6.4 and 6.5 in the next video, and that will be it for chapter 6, and I hope to see you in the next video.